So in linear algebra, on page 262, these are problems about rotations and reflections. So for example, if we look at number 1, we're considering a rotation.
Excuse me, Professor, 254?
254?
Yes.
Okay,
Thank you.
let's look at page 254. And which number?
Number 1 or number 2?
Okay. So on page 254, if you look at number 1, we have a linear operator from R2 to R2, and it's defined by t applied to the vector xy is 5x minus y, 3x plus 2y. And we want to compute the matrix with respect to the standard basis where you have the vector E1 is 1, 0, and the vector E2 is 0, 1. So if I take t of 1, 0, when x is 1 and y is 0, we get 5, 3, which is exactly, so this is t of E1, which is the same as 5, 0 plus 0, 3. So this is 5 times 1, 0 plus 3 times 0, 1, or 5E1 plus 3E2. And t of E2 is t of 0, 1. When x is 0 and y is 1, you get minus 1, 2, which is minus 1 times 1, 0 plus 2 times 0, 1. That's minus 1 E1 plus 2 E2. And so if we were to write the coordinate vector of t of E1 with respect to this basis, it would just be 5, 3. And the coordinate vector for t of E2 with respect to this basis is minus 1, 2. So the matrix for t with respect to this basis is, the first column is 5, 3, minus 1, 2 is the second column. Just what you would expect, in fact. So that's the matrix for t with respect to the standard basis. That's all it is. The interesting thing is when you take a different basis. So if we take the basis B1, it consists of two vectors, 11, 0, and 0, 7. So maybe I'll call this vector F1 and this vector F2. Then t of F1, that's t of 11, 0. When you let x equal 11 and y equal 0, you get 55, 33, which is exactly which is when x is 11 and y is 0, I get 55, 33. So with respect to the standard basis, let's see, what is this? Sorry, with respect to this new basis, this is 55, 0 plus 0, 33. So this is 5, times 11, 0 plus something times 0, 7. It looks like it's 33 over 7 times that. So as a linear combination of F1 and F2, T of F1 is 5 times the vector F1 plus 33 over 7 times the vector F2. So let me just explain what's going on in case this isn't clear, just in general. You have a linear transformation from a vector space V to W, and you have a basis let's say B sub V is a basis for the vector space V. So let's say it consists of the vectors E1, E2, up to E sub n. And suppose W has a basis V sub W. Let's say the dimension of V is n, and the dimension of W is m. So we have a basis V sub W for this vector space W, which consists of, let's say, the vectors F1, F2, up to F sub m. So T of any of these vectors, E sub j, is going to be some vector in W, some linear combination of the basis vectors for W. This is going to be of the form Aij F sub I goes from 1 up to m. You take a vector in V, it ends up in W. Every vector in W is a linear combination of the vectors in the basis. So some linear combination Aij Fi, so T of Ej is something, it looks like this. So what this means is if you write the vector T of Ej, what is the coordinate vector for this? What are the coordinates with respect to the basis in W? These are the coordinates, these numbers. It's going to be A1j, A2j, down to A sub mj. This is the coordinate vector for T of Ej in the vector space W. And the matrix for T, so this is the matrix for T with respect to these bases, is the matrix Aij. That means these are the columns. Like the first column would be A11, A21, down to AM1. Second column is A12, A22, down to AM2, all the way up to the nth column, which is A1n, A2n, down to AMn. So this is the matrix for the linear transformation T with respect to these bases. So, and this is going to depend on the basis. When you change the bases, you change the coordinate vectors and you change the matrix. Right? That's what's going on. So here I have this linear transformation from R2 to R2. If we take the standard basis, the matrix just always turns out to be exactly the matrix of coefficients, 5, 3, minus 1, 2. That's the matrix with respect to the standard basis. But when you change the basis, you change the matrix. So if we take the new basis, 11, 0, and 0, 7, T of this first basis vector, F1, that's T of 11, 0, you get 55, 33. And then I need to write this as a linear combination of F1 and F2. This is 55, 0, and 0, 33. 55, 0 is 5 times the vector 11, 0. 0, 33 is 33 over 7 times the vector 0, 7. And if I take T of F2, that's T of the vector 0, 7, when x is 0 and y is 7, I get minus 7, 14. This is minus 7, 0 plus 0, 14. Minus 7, 0 is minus 7 over 11 times the vector 11, 0. And 0, 14 is 2 times the vector 0, 7. So this is minus 7 over 11 F1 plus 2 F2. And so the matrix T with respect to this basis B1, the first column is going to be 533 over 7. And the second column is minus 7 over 11, 2. So that's the matrix. Then we do the third part, part C, which is the most interesting part, I guess. So again, we have, so this is 1C. Again, we have this linear transformation. T of xy is 5x minus y, 3x plus 2y. And I'm taking the basis B, which consists of two vectors, 1, 1, and minus 1, 1. So maybe I'll call this G1 and this G2, just to give them names. So what is T applied to the vector G1? That's T of 1, 1. When x and y are 1, you get 5 minus 1 is 4, 3 plus 2 is 5. I get 4, 5. But I want to write this as some linear combination of my basis vectors. I want to write this as A11 G1 plus A12 G2. I'm solving two equations, sorry, A21 G2. So that's the same as A11 times the vector 1, 1 plus A21 times the vector minus 1, 1. So this is equal to A11 minus A2 minus A21, A11 plus A21. So linear algebra often reduces to linear equations. I have to solve these equations. A11 minus A12 minus A21 equals 4. A11 plus A21 equals 5. And if I add those equations, I get 2A1 equals 9. So A11 is 9 halves. And if I subtract the second equation from the first, I get 2A21 equals 1, or A21 equals a half. And again, you can check if you add them, you get 5. If you subtract them, you get 4. So the matrix, right? So in this matrix for T, the first column, which is A11, A21, is going to be 9 halves, 1 half. And then I have to find the second column. So I take T of G2. So that's T applied to the vector minus 1, 1. When x is minus 1 and y is 1, I get minus 6. When x is minus 1 and y is 2, I get minus 1. Minus 5 minus 1 is minus 6. Minus 3 plus 2 is minus 1. And I want to write this again as some linear combination of the vectors G1 and G2. This is going to be A12 times this and A22 times this. So this is A12 minus A22, A12 plus A22. So I have to again solve the system of linear equations. A12 minus A22 is minus 6. A12 plus A22 is minus 1. If I add these equations, I get 2A12 equals minus 7. So A12 is minus 7/2. If I subtract the equations, I get 2A22 is 5, and A22 then is 5/2. Let's see, if I take this minus this, I get minus 6. If I take this plus this, I get minus 1. So the second column of my matrix is going to be minus 7/2, 5/2. So when I calculate the matrix for this linear transformation with respect to the basis, this is my answer. So the basic object in linear algebra is a linear transformation between vector spaces. And the major fact is that once you specify your basis for your vector space, the linear transformation is just a matrix. And the matrix depends on the bases, and you have to be able to calculate it, and you just did in this case. So that is problem 1. So this is linear algebra on page 279, which has to do with eigenvalues and eigenvectors. So if we have a linear operator, linear transformation from a vector space to itself, you say that a scalar lambda is an eigenvalue of this operator T if there is a non-zero vector V, which is called an eigenvector for lambda, such that if I apply T to this vector V, it doesn't change its direction, it just stretches it by a scalar lambda. So T of V is just some scalar times V. That's the definition of an eigenvalue and an eigenvector. Lambda is some real number, and V is a non-zero scalar. So we want to, on problem 1A, this is on page 279, we want to find the eigenvalues and the eigenvectors for the linear operator T from R2 to R2 given by the matrix 1 minus 1, 2, 4. So that means T, so T is an operator from R2 to R2, and T of xy is just the matrix 1 minus 1, 2, 4 applied to xy. That's x minus y, 2x plus 4y. That's what T of xy is. If T is the operator defined by this matrix. But we want this to be an eigenvalue, an eigenvector, and an eigenvalue. So we want to know, one, does there exist a lambda such that this vector is really just lambda times xy, which means lambda x, lambda y. So we want to know for what value lambda can you find x and y that solve this equation. And it's a vector equation. So x minus y has to equal lambda x, and 2x plus 4y has to equal lambda y. Now, this is just a homogeneous system of two equations and two unknowns. You might say, well, where's the homogeneous system? Where is it equal to 0? So just collect your x's and your y's. So this is, for example, like lambda x plus x, I get lambda plus 1x plus y equals 0. I'm just rewriting the equations. Minus 2x plus lambda minus 4y equals 0. Right, so now I've reduced this all to just high school algebra. These two equations are the same as these two equations. And this is a homogeneous system of two equations in x and y. And we want to know for what value of lambda can you find a non-zero solution of these equations. So if you have a solution of these equations, if you just look at the first equation, for example, it says, let's see, for what value of lambdas can you solve these equations? What can we do? If we multiply the first equation by lambda minus 4, again, I just want to eliminate the y. So I get lambda minus 4 times lambda plus 1x plus lambda minus 4y equals 0. And I multiply, and I don't do anything to the second equation. I just leave, I can leave this minus 2x plus lambda minus 4y equals 0. If I subtract the second equation from the first equation, I get lambda minus 4 lambda plus 1x plus 2x equals 0. Or lambda minus 4 times lambda plus 1 plus 2 times x equals 0. And if I want to find a solution where x is different from 0, then this has to be 0. This is what? This is a quadratic equation. If I expand it, I get lambda squared minus 3 lambda minus 4 plus 2 minus 2 equals 0. So let me just check my algebra here. I have my matrix 1 minus 1, 2, 4. So if I apply that to a vector xy, I get x minus y, 2x plus 4y. And I want to know when is there a lambda such that for some non-zero xy, this is just lambda times xy or lambda x, lambda y. So if I compare the first coefficients, x minus y has to be lambda x, which is the same as lambda plus 1. Sorry, I'm always glad. Let me see, I made a mistake. It should be lambda minus 1x plus y is 0. And when I compare the second coordinates, 2x plus 4y equals lambda y, that's this equation. This says minus 2x plus lambda minus 4y equals 0. So if I multiply the first equation by, I want to cancel the y's, let's say. I multiply the first equation by lambda minus 4. So I get lambda minus 4 times lambda minus 1 times x plus this. And here's my second equation. And if I subtract, these terms cancel. So I get this minus this. Lambda minus 4 times lambda minus 1 plus 2x, or lambda minus 4, lambda minus 1 plus 2 times x is 0. And if I multiply this out, I get a quadratic equation, lambda squared minus 5 lambda squared minus 5 lambda plus 4 plus 2 plus 6 equals 0. So if there's going to be an eigenvalue lambda, it has to solve this quadratic equation. And you know how to solve a quadratic equation. There's always the quadratic formula, or you might see this factors. This is lambda 2 minus lambda 3. So the solutions are lambda equal 2 and lambda equal 3. So these are the only possible eigenvalues for this problem. All right, so again, before I go, I still haven't solved the problem. This is just the first half. So let me just explain one more time what's going on. I have a linear operator T from R2 to R2. It's given by this matrix. In general, if you have a linear operator from one vector space to itself, a number lambda is called an eigenvalue for the operator if there's some non-zero vector v such that T of v is just some scalar multiple of v. T of v is just lambda v for some lambda. And such a lambda is called an eigenvalue, and any vector that satisfies this equation, any non-zero vector that satisfies this equation, is called an eigenvector. So we want to solve this linear algebra equation and find the lambdas. So I want to know if this is my linear operator, T of xy is this vector. And if that's going to be lambda times xy, then lambda and x and y satisfy these equations, which means that if lambda and x and y satisfy these equations, then this is the case and this is the case. And we get that, well, we just solve this. We get this equation and lambda and x, it's something times x is 0. And if the lambda is a root of this expression, then it can be an eigenvalue. This expression is just a quadratic equation in lambda. This equal to 0, lambda is 2 or 3. So let me just say exactly now where we are again. We're still working on the same problem. We have T from R2 to R2 given by T of xy. It's this matrix 1 minus 1, 2, 4 times xy, which is x minus y, 2x plus 4y. And the only possible eigenvalues, the two possible eigenvalues, let's say the first one is 2 and the second one is 3. Because those were the roots of that equation, the quadratic equation. So let's find, if we can, an eigenvector for lambda 1 equal 2. This means a vector such that T of xy is lambda 1 xy, or 2 xy. We want to find a vector that satisfies this equation. Of course, T of xy is x minus y, 2x plus 4y. And we want that to be equal to 2x, 2y. We want T of xy to be 2x, 2y. So we want to solve the equations x minus y equals 2x, 2x plus 4y equals 2y. This first equation is equivalent to x plus y equals 0, and so is the second equation. So y has to equal minus x. So if I take any vector v, which is x, y equal to x minus x, or any scalar multiple of 1 minus 1, that should be an eigenvector. So I claim, for example, that 1 minus 1 is an eigenvector with eigenvalue 2. Lambda 1 is 2. Let's check. If I take t of 1 minus 1, that's equal to 1 minus minus 1 over 2 times 1 plus 4 times minus 1. This is 1 plus 1 is 2. This is 2 minus 4 is minus 2. This is exactly 2 times 1 minus 1. So if I let V1 be 1 minus 1, I see that T of V1 is 2 times V1. This says that V1 is an eigenvector with eigenvalue 2. Suppose I want to find an eigenvector for the eigenvalue 3. That's the second possible eigenvalue. So if T of xy is x minus y, 2x plus 4y, that's going to be 3 times the vector xy, or 3x, 3y. That means I have to solve the equations x minus y equal 3x, 2x plus 4y equal 3y. Let's see, the first equation is equivalent to 2x plus y equals 0, and so is the second equation. So y has to be minus 2x. So if you take a vector xy, where y is minus 2x, this is just some scalar multiple of 1 minus 2. So if I let the vector v2 be equal to 1 minus 2, t of v2, that's t of 1 minus 2, what is that? If I put 1 minus 2 into my definition of my operator t, 1 minus minus 2 is 3. This is 2 minus 8 is minus 6. I get 3 minus 6, which is exactly 3 times 1 minus 2, or 3 times my vector v2. So T of v2 is 3v2. And I found an eigenvector for the eigenvalue 3. So this is, there's a lot of algebraic calculation involved, but in linear algebra, if you pursue it further, because we're just really beginning the subject, the study of eigenvalues and eigenvectors is very, very important in applications and in theory. So you're saying go back to this line right here?
The line before that?
Up here?
Yeah, to the left.
To the left, okay.
Where did that come from? Where we, like that sequence, like where did that come from?
Good question. So here's my linear operator from R2 to R2. If you apply t, the operator t, to the vector xy, this is the definition. This is what we're given. T of xy is defined by this matrix. So t of the vector xy is the vector whose first coordinate is x minus y, and whose second coordinate is 2x plus 4y. And I want to find eigenvalues and eigenvectors for the linear operator. So what I calculated on the previous page told me that the only eigenvalues, certainly the only possible eigenvalues, were 2 and 3. So I only have to look for eigenvalues 2 and 3. So let's look at 2. So suppose I let lambda 1 be the number 2, right? This is the first case we're considering. Right? This is the case lambda 1 equals 2. So I want to find the vector xy, where t of xy is 2xy. T of xy is this vector. And 2xy is this vector, 2x, 2y. So when you compare the first coordinates, you get this equation. And when you compare the second coordinates, you get this equation. This is the same. This equation, let's just rewrite it. This is x plus y equals 0, and so is this. So if you're going to have an eigenvector for lambda 1 equal 2, for that eigenvalue, y has to equal minus x. So your eigenvector must be, if it's xy, but y is minus x, it's really x minus x, which is x times 1 minus 1. So any eigenvector must be a scalar multiple of 1 minus 1. You take 1 minus 1, 2 minus 2, 7 minus 7. They're all scalar multiples of each other. But so I want to show that this is in fact an eigenvector with the eigenvalue 2. So this is just my check. What is t applied to this vector 1 minus 1? When I put it into my formula for t, I get 2 minus 2, which is 2 times 1 minus 1. 1 minus 1 is this vector v1, so t of vector v1 is 2 times v1. That means, and v1 is not the 0 vector. So this means that that means that 2 is an eigenvalue, and the eigenvector for 2 is this vector v1 or any scalar multiple of it. That's where it all comes from.
Okay, thank you.
So this is still linear algebra. And these are problems on inner products in Rn. And this was the last homework. This is on pages 304 to 306 probably. Number 1. So we have to know what is an inner product. So the standard inner product, so if you took Calc 3, you will have seen this, at least in R2. If you take a vector x1, x2, or maybe I'll call it, doesn't really matter what coordinates we use. And v2 is, maybe I'll call this x1, y1, and v2 is x2, y2. The inner product, v1, v2, you multiply the first coordinates, you multiply the second coordinates, and you add. That's the inner product. And you do this in calculus, all the time. If you have v as the vector xy, if you take the inner product of v with itself, you get x squared plus y squared, which you know from geometry. This is x, this is y. You have this right triangle. This is the square root of x squared plus y squared. So this is the square root squared. This is the length of the vector v squared. This is just high school geometry, Calc 3. This is the inner product. And what you learn about the inner product is that the inner product of v1 and v2 can also be written as, so let's say you have two vectors, v1 and v2 in the plane. The inner product is the length of v1, that's what these double arrows mean, and the length of v2 times the cosine of the angle theta between them. That's the inner product. Now, of course, you know that the cosine of theta is 0 if theta is, for example, plus or minus pi over 2 radians. So another way, so you can define now what it means for two vectors to be perpendicular. Because two vectors are perpendicular if this angle is pi over 2. which is the same as the cosine being 0. So non-zero vectors are perpendicular. And again, in mathematics, sometimes someone says normal. It's a synonym for perpendicular, or orthogonal, which is another synonym for perpendicular. If they're in a product, V1 and V2 is 0. It's the only time, if you have two vectors that aren't 0, so their lengths are positive, the only time the inner product is 0 if the cosine of the angle between them is 0. And that only happens when the angle between them is plus or minus pi over 2 radians. So perpendicular vectors have inner product 0. We also say that non-zero vectors are parallel if one is a scalar multiple of the other. It can be positive or negative. So you have this vector and this vector, they're parallel. And this vector and the same vector going off like this, these are parallel. Here this might be plus c, here this might be minus c. But these vectors are parallel. And one of the things that you do in geometry, and you certainly do, for example, in physics, is if you have a vector v1 and another vector v2, you often want to write v2 as a sum of two vectors, one of which is parallel to v1 and the other is perpendicular to v1. Maybe instead of v1 and v2, I'll call this vector v, and I'll call this vector w. And I want to write the vector w as a vector which is parallel to v plus a vector which is perpendicular to v. Right? I mean, this is the symbol for perpendicular. This is the symbol for parallel. So I want to write a vector w. I'm going to have a piece parallel to v and a piece perpendicular to v. So we would say this is the component of w parallel to v, and we would say this is the component of w perpendicular to v. And the question is, how do we find these things? So, I mean, the only time perpendicular makes sense is if you have this inner product. And suppose I take the w parallel. So w parallel, if this is going to be a vector parallel to v, this has to be some scalar multiple of v. And suppose I take the inner product of v and w divided by the inner product of w with itself, the inner product of v with itself, times v. So v is a vector, the inner product is a number. So this is some scalar. And the inner product of v with itself is just the length of v squared, which is positive because we're taking non-zero vectors. So this is certainly a vector parallel to v. And suppose I define W perp to be W minus this piece, which I'm going to call the parallel component, W minus this thing. So this is going to be W minus the inner product of V and W divided by the inner product of V with itself times V. And I claim that this vector is perpendicular to V. So suppose I calculate the inner product of V and W perp. So that's the inner product of V with this vector, W minus the inner product of VW over the inner product of V with V times V. And the inner product is almost like a linear transformation. This is going to be the inner product of V and W minus the scalar VW over VV times the inner product of V with itself. And if this is correct, these numbers cancel and then these cancel, and I get 0. So this vector is perpendicular to V, and from this equation I have W is W parallel plus W perp. So I've written W as a sum of two vectors, one parallel to V and the other perpendicular to V. So that's just the background of this. And on page 304, 305, number 1, I have the vector V, which is 3 minus 1, and the vector W, which is 2, 2. I mean, what does that look like in the plane? Here's 3 minus 1. That's the vector V. The vector 2, 2 is over here. That's the vector W. And I want to write W as a sum of a vector parallel to V and perpendicular to V. That is, if I were to draw this right angle, this piece would be the component of W parallel to V, and this piece would be the component of W perpendicular to V, and this plus this add up to W. So W parallel, this is equal to the inner product of V and W divided by the inner product of V with itself times V times V. What is that equal to? Here's V and W. So the inner product of V and W, you multiply the X coordinates, you multiply the Y coordinates, and you add, you get 6 minus 2, that's equal to 4. The inner product of V with itself is 3 times 3 plus minus 1 times minus 1. That's 9 plus 1, or 10. So this vector is 4 over 10 times the vector 3 minus 1. This is 2/5. So this is 6/5 and minus 2/5. So the vector W11 is this vector, 6/5 minus 2/5. And the W perp has to be W minus W parallel. W is 2, 2, and I'm subtracting 6/5 minus 2/5. So this is 10 minus 6, this is 4/5, and this is 10 plus 2 is 12/5. So if I did this correctly, this is W perp. So let's just check. If I take W parallel plus W perp, this is equal to 6/5 minus 2/5 plus 4/5, 12/5. That's 10/5, 10/5, which is 2, which is W. So that checks. And what is the inner product of V and W perp? So V is 3 minus 1, and W perp is this. So if I take the product of the coordinates, I get 3 times 4/5 plus minus 1 times 12/5. That's 12/5 minus 12/5. That's 0. So everything works out perfectly. I have W as the sum of these two vectors. This W parallel is a scalar multiple of V, so this is parallel to V. And if I take the inner product of W perp with V, I get 0. So W perp is really perpendicular to V. And that's high school geometry. Just drawing a right triangle. I started out with this vector and this vector. And when I write this vector, I'm going to have a right triangle where one leg is parallel to V and the other is perpendicular to V. I did it.